There, chemists. In this lesson, we are going to look at some interesting things we can do with alkynes. And the first thing I have on your screen is a picture of a molecule called caliciamycin. This is a naturally occurring molecule, and it's one of the few natural products that has an alkyne in it. There's a piece up here that's called an ene diene, and you can hopefully see where that name comes from. It's an alkene with two alkynes, so ene diene. It's believed that this ene diene undergoes a special type of cyclization, which I'll show you right here, a generic ene diene, that forms a diradical on a six-membered ring. That looks like that. You get to that arrow pushing with a bunch of fishhook arrows, and it's believed that this causes strand scission. In cancerous DNA. And that's a good thing. This is how this acts as an anti-cancer agent, or anti-tumor agent. It's isolated from bacteria, and chemists, remember the whole point of this class is chemists are interested in making molecules for the benefit of society. This is how we get at some of the most interesting and useful drug molecules that we have. It's because we can make them. And many times we learn from naturally occurring molecules like the caliciamycin molecule that you have in front of you, and there's a whole series of ene diene derivatives that have been made modeled off of this to try and find new anti-tumor agents that are just as good or even better than what we get from nature. So the focus of today is alkynes. What can we do with them? And to start off, let's look at how we make alkynes. There are two ways I want you to know that you can make an alkyne. They both come from alkenes. The first one involves two steps. It's a halogenation with bromine. That's earlier from this class. And then you can do a double elimination with just a strong base from our previous unit. So this is halogenation, adding, in this case, two bromines across the pi bond, and then a double E2. Because you can imagine having a bromine with a beta hydrogen and losing that bromine and that hydrogen, and then you have a second beta hydrogen relative to the other bromine atom, and if you lose both, like so, or sorry, KOH takes the H, CH bond breaks, bromine leaves, and then do it again, you get not one, but two pi bonds, in other words, an alkyne. The second way uses the reaction we just learned in the previous lesson. This is an ozonolysis, followed by a special reaction called the Corey-Fuchs olefination. This is a multi-step reaction, 3 steps, that turns an aldehyde into a terminal alkyne. The steps are carbon tetrabromide with triphenylphosphine, followed by a base, followed by a source of acid or just water. This one is less atom economical. You actually cut a carbon off. We lose one of those carbons as formaldehyde. So you take a 3-carbon alkene, you get a 2-carbon aldehyde, and then you put the carbon back on from carbon tetrabromide. But it works quite well, although specifically this is for terminal alkynes only. Terminal alkyne. Speaking of terminal alkynes, that's going to be our focus of today. Once we make alkynes, how can we use them? It's all about making what's called an alkyne anion. If you have a terminal alkyne, meaning at the end of a chain, you can deprotonate it with a really strong base, super strong base. This is essentially Na plus and NH2 minus. And that can take away the alkyne H. That's a CH bond. And you'll generate an alkyne anion. And terminal alkynes can be deprotonated to make this carbon anion. This is a carbon nucleophile. So we can use this in a variety of reactions. Good review of acid-base chemistry, why this actually works. Remember, your pKa of a terminal alkyne is roughly 25. NH2 minus takes that H away, and you actually make an equivalent of ammonia. So if you compare pKa values, 25 for the alkyne, roughly 40 for the ammonia molecule, so the equilibrium lies in that direction. We could not do this with hydroxide. Hydroxide is not basic enough to take away that H. If we imagined what it would look like, you would be comparing the pKa of 25 with the pKa of something like water, which is only 16, and the equilibrium would go to the left. So we need a very strong base to do this. This is actually the conjugate base of a base. This is the anion of a weak base, ammonia, NH3. All right, so what can we do with this? There are three things that we can do with an alkyne anion where we use it as a nucleophile. Number one, we can do SN2 reactions. So nothing new today other than a new type of nucleophile. So I'm going to redraw that alkyne anion now that we've made it, and just show a generic SN2 reaction. That might be with any SN2 acceptor. Negative charge hits the carbon, leaving group leaves. That means you turn your terminal alkyne into an internal alkyne. So later on, as we start to do synthesis problems, we'll ask ourselves, how do you make an alkyne? And the most common answer to how do you make an alkyne is from an alkyne. You start with a shorter alkyne and you make it larger. Secondly, the second thing we can do is we can add it to ketones and aldehydes. Addition to ketones and aldehydes. So I'm going to use this same anion as an example. And let's draw a generic ketone. I'll just use acetone. Now we've seen things like carbonyl compounds and ketones react with other carbon nucleophiles, like things from the SN2 days. It's no different here. The anion will attack the carbonyl carbon, and the dipole goes up to the oxygen. Remember, oxygen is the second most electronegative element on the table, so there's already a pre-existing dipole, so that carbon feels a little bit more positively charged. So what do I get? Well, I have my three carbons that used to be the alkyne, a new carbon-carbon bond, there's two methyls along for the ride, and now a single bond with an oxygen and a negative charge on that oxygen. We don't keep that as an oxygen anion. There's a second step to this where we throw in what's called an acidic workup. So anything that acts as a source of H+ can protonate that oxygen anion, and you have a new way of making an alcohol. This is called a propargylic alcohol. That just means it's one away from an alkyne. Remember, allylic means one away from an alkene. Propargylic is the analog for alkyne chemistry. And I wrote addition to ketones and aldehydes. Imagine what this would be if I just had an aldehyde in the beginning. You would get the same outcome. I would just have an H along for the ride and an H along for the ride. So I would get a different type of alcohol, but the same type of chemistry would happen. The third and last one for this is addition to another oxygen-containing electrophile, epoxides. Addition to epoxides. So let's use the same alkyne, and then show a generic epoxide. I'll make it slightly substituted. Remember, we can make epoxides with an alkene and MCPBA. Epoxides are electrophilic. They are strained. They're a little three-membered ring, and they're electron poor because of that oxygen atom taking electron density away from those two carbon atoms. Now, this nucleophilic carbon sees both of those carbons attached to the oxygen because they both experience this dipole, but which one does it attack? Well, it goes for the less substituted carbon atom. So draw an arrow from that negative charge to the less substituted carbon of the epoxide. That breaks the carbon-oxygen bond. You have your triple bond from the original alkyne. You have a new carbon-carbon bond, and then every carbon that was along for the ride that used to be part of the epoxide. And similarly to up above, we get an oxygen anion. So there's a second step in acidic workup that we protonate get an alcohol. This is actually similar to a propargylic alcohol, but it's homologated. It's 1 carbon lengthier. So they actually call this a homopropargylic alcohol, where that means homologated, 1 extra carbon, 1 more carbon away. Make a note about what we showed but didn't write in words. Anion attacks less substituted carbon. Less substituted side of epoxide. Okay, so that's how we make alkynes, starting with alkenes. We can deprotonate them to make alkyne anions, and these turned out to be fantastic building blocks to make a variety of alkyne-containing functional groups, which we can then functionalize using any of the other alkyne reactions we've learned.